Good afternoon and welcome to another edition of VisualSim webinar series. Today's topic is on power. The title is Accurate System Level Power Measurement Challenging? Is it for everyone, and how can it be effectively created within your environment? I'm Deepak Shankar, your host today, and I'm the founder and CEO of MIRABILIS Design that is bringing you this webinar. Today we will start in about 3 minutes, just allowing for people to settle down, and a few more people are joining us. So please bear with me for about 3 minutes and then we'll start right away. Thank you for your patience. We would like to get started right now. Welcome one and all to the VisualSim Power Webinar series, Is Accurate System Level Power Measurement Challenging? I'm Deepak Shankar, your host for the day, and I will be walking you through a maze of elements that go to form power analysis at the system level. Now, before I get started, there's a couple of logistics issues. We would like you to remain on mute. The reason being that there's a number of people on the session, and if there's any sort of disruption, it might spoil the overall challenge for them to be able to be heard clearly. Now, with regards to asking questions, on your console panel on the right-hand side, if you click on this double arrow, it'll expand to see a view here where you have a chat space. Click on this down arrow and you can actually type in any questions. As people type in questions, there's about 3 people waiting that can instantly answer your questions. The questions will be answered in the order that they receive. With this, I'd like to go ahead and start the presentation. The purpose of this webinar was to really help people understand system level power exploration. What is the impact? How do you do it? And what are all the other peripheral things that get impacted as a result of system level power analysis? Today, we are not just going to talk about it, but actually show you firsthand how it has impacted real systems. Now, a quick background of MIRABILIS Design. We're a provider of modeling and simulation software which helps you do architecture exploration, power analysis on systems, semiconductor, and embedded software. The product is called VisualSim Architect, and the company is based in Silicon Valley, right in Sunnyvale, and almost everybody in the company has extensive experience in system modeling, architecture exploration, and power measurement. One of the things that makes us the leader in the system level modeling space is the source of system modeling IP, which is probably the largest in the industry today. Our product is VisualSim. It's a completely graphical and hierarchical modeling environment where you can do hardware software partitioning, architecture exploration, performance, and power analysis. And it can actually encompass your full system. A system is what it is that you're building. So it can be a semiconductor, an SoC, a processor, network switch, can be a high performance computer, can be a router, can be a camera, can be any of these combination of things as well. The tool actually has a large library of pre-built components that have timing, power, functionality built into it. To give you a quick understanding of what this product is, this is the environment that you're seeing, which is VisualSim Architect. See the libraries here, and you have the system construction environment, and you have a model simulating button here, which generates a series of parameters and, series of plots. You can vary attributes of your system and then do a variety of analysis. Now, a quick introduction to power modeling. Power modeling at the system level is a relatively new phenomenon. Most people tend to focus on power modeling as something that they can do in Excel, where they can generate either worst case or best case, or kind of take average values and come up with a power number. One of the things was that it was fine in the past when power was not that critical, and most of it tends to be leakage power. Now, as we move away from a leakage problem and starting to move more to a performance-oriented power, be it on a satellite or on a semiconductor, the heat dissipation, which is going to be effectively your cooling effects, the length of your battery life, your power performance trade-offs, all of that have a huge impact on your product quality. Also, a new trend is being able to do power and performance or time-based analysis within the same model or within the same environment. Examples of power investigation can be where I want a voltage and frequency scale based on the amount of power available in the battery or amount of charging on my solar panel, looking at what happens if I change the power management or control logic, implement power gating, be able to do comparison between different architectural topologies. Now, let's take an example of why a simulation-based power analysis is far more critical relative to a spreadsheet-based approach. Today, if you take a spreadsheet, which in this particular case is an ARM-based imaging equipment, you would add up all the power here, put it on a table, and then you take the average of those and then add them up to a single number. Now, this is fine to give you an average load over the entire period of the system operation. But now, when you take up simulation, in simulation you're running your workload, your use cases, and other attributes where if you look at the exact same architecture but simulated now, you will see that the power has actually got modified as a result of how the use case is executing concurrent operations. So certain of them are in active states, certain of them might be in standby or wait state, things like that. So allows you to really evaluate what is happening to your overall power activity. So the average, if you look at the averaging or the analytical method, it's starting to lead to a lot of incorrect expectation where you get from simulation a more accurate result over time. Now, if you look at dynamic system level power profile, there are three different attributes you want to look at. What is the instant power at each clock cycle? What is the average power over time? And of course, what is your peak power? Each of these play a major role. The average can help you determine what your battery is going to take. Your peak is going to determine what your cooling is going to cost. And then the instantaneous is going to tell you what is going to be the degradation of your battery or how much of solar panels you need for charging your system. So the dynamic nature of system level power profile really lends itself to be able to make a number of architectural decisions. As I mentioned before, questions can be asked at regular intervals. There are other people standing by, so feel free to ask your questions as we go along, and these people can go ahead and answer your questions. Now, let's take a step back and look at what is system level power analysis. System level power analysis is really looking at the power of your entire target design. Your target can be a processor, can be a comm device, can be a spacecraft, or a high performance computer. The other attribute is that with power, you really want to look at use cases and workload over time, which is something that you would normally not focus on, focus more on the power of each individual component. This is really looking at the total power of the system. The other piece of it is varying the configuration and running a large number, probably 500,000, 2,000 of these, and then get results back in a very, very short period of time. The other piece of it is the power is another requirement or another measure that needs to be provided to both the design team and to marketing. The marketing for obvious reasons to be able to promote what this future product is going to look like. Design teams so that they can plan ahead both the mechanical design and the electrical design on how their system is going to look like. The other piece of it, and I'm going to talk about this in a little more detail, which is really creating a multi-dimensional system evaluation platform. Coming up with how do I create my better quality product using the singular platform, where I look at all the different attributes that go to form my system. Now, a quick question on how can system level power analysis really aid your development? There are a number of different things it can help. Probably the first and foremost is hardware-software partitioning. How do I determine what's going to be the clock speed of my system? What are going to be all the peripheral components? What is going to be the IPs that I select? The other part of it is on the software, which is really looking at software scheduling versus how the power profile changes. Like for example, if I run them all concurrently versus I shift them with an offset, what is the impact? The other one is really looking at power feasibility. A lot of products today are failing just because they're not able to meet the power budget, either because the pre-provided power cord has only 220 watts of power, or the cooling available is not sufficient for this SoC to be placed inside the clamp or the socket. The other aspect, which is really the confidence. How do I look beyond just my static power? How do I look at the dynamic power? And as you move to lower nanometer geometries, the dynamic power is going to be more and more critical. So you have to understand that before you can actually put in your architecture. The last one is really looking at the power management. How do I shut down different systems? Like for example, on a car, how do I shut down the entire network? Or for example, in say for example in like say in a chip, how do I change the burst rates for reads and writes to the DDR3 memory so that I can reduce the power on my memory controller? So looking at all of this, let's take a shift and look at a power analyzer. What are the attributes you need? There are really three attributes. The first is your architecture, which is really your hardware platform. The second is your behavior, which is your use case and your workload. And the third is the spreadsheet containing the combination of devices and the values, the power values for each state and the transition cycles for inductance and for capacitance. Out of this comes a variety of plots. In this particular case, what they are is you're looking at the latency or the time taken to complete each of the tasks. Each task is identified by its unique color. What is the power consumed by each device in that system? And at the same time, looking at the cumulative power and the utilization of different hardware components. So really looking at all of these within a single environment is really a power performance trade-off. Now, that is one aspect of it. The other aspect of it is really trying to understand the impact, a very detailed activity within your system and how they translate to power. In this particular case, what are we looking at is we're looking at a memory subsystem. And as you can see, those are the activates, the reads, and the writes, and the refreshes. So what I can do is as I zoom into a region over here where you can see that's my LPDDR read right here. That's the bidirectional bus, and that's the activity on the banks itself. Those translate into the power consumption right over here. The activate translates into your recharge and your activate, the RAS, the RP, the RCD. These translate into like write to read, the read cycles, the write cycles, and of course these are your regular refresh cycles. Now, if you look at this, you can actually see what you're seeing over here is the blue demarcates what the power consumed is for each individual cycle. And you can see, where the peaks are and also what the average power is. Now, with regards to this, I'm going to move over to a short demonstration to show you how these two types of analysis really play out. The first one we're going to look at is a system on chip. And in this particular case, what we have is a memory subsystem, an ARM subsystem connected to an AXI bus to an SDRAM and a flash. These are standard components that are in the VisualSim modeling library that you drag and drop and you assemble it. What I'm going to do is go ahead and click on the Go button, and it's going to go ahead and run a simulation. What we're seeing over here is a series of building blocks that go to form the use cases. These use cases are associated with the different operations of this particular device, or the different tasks on these devices based on some workload or some image coming into the system. Initially, all of these are implemented on the ARM subsystem. So as I look at the timing diagram, what you're going to see over here is you're going to see the power spikes initially and then it levels off. What you're also going to see here is the number of macro blocks I can complete, which I notice my peak here, 10 to the power 3, is 6,600. Now, our particular goal in this particular architecture is we need about 13,000 macro blocks within this 20 milliseconds, and we've got to have the power to be less than 1 watt of power. Now, based on all of our analysis, we have found that the rotate frame, which is some of the other statistics I'm not going to go into, is the one that's consuming a lot of CPU cycles. So what we're going to do here is we're going to change this and make it into run hardware, which means it's going to run on a hardware accelerator right over here. So we're going to go ahead and modify it where the mapping now from this behavior to the architecture is moved to a hardware accelerator for only the rotate frame. So you're going to go ahead and rerun the simulation and taking particular visualization of these two components here. One thing you notice right off the bat is that the power consumption, which was dipping here and below 1 watt, it is actually increasing, going over about close to about 1.5 watts of power. So almost a 50% jump in power. Now, if we look at the frames completed or the macro blocks completed, it's about 14,000 macro blocks within the 20 milliseconds. Now, if you look at how long it took to run the simulation, it took less than 36 seconds. 36 seconds for 20 milliseconds of an image processing system. Now, this again doesn't meet our requirement because we're at 1.5 watts of power. We really need to be less than 1 watt. Now, here we have a little bit of cushion because it's 14,600. We really only need 13,000. What we're going to do here is add one more element, which we're going to make the hardware accelerator to go into power gating mode. In this case, it's a very strict power gating in the sense the moment the operation completes, it's immediately dropped to a sleep mode, just like this. So right here, it completes a processing, immediately drops to a sleep mode. So very little, just the leakage power. One of the things you notice right off is that the power consumed here drops back below the 1 watt of power. Now, obviously the video frame is not able to reach the 14,600, and what we see right now is that I think it finally drops to about 13,300. So what is happening now is we've got a drop of about 1,100 frames, about 6 to 7% macro blocks that have been lost, and that's because of the entire power gating and the transition cycles and for loading in the cache and things like that. So as you can see, the simulation allows you to be able to analyze and to evaluate the performance of your particular architecture, making particular reference to the power consumption. Now, exact same design. The only difference we're going to do now is we're going to take a different type of a design, which is where it only focuses on one subsystem, which in this particular case happens to be the dual channel DDR memory. So what we're going to do here is we've got dual channel, which is the memory controller 1 and 2, has very detailed memory information and a power table right over here. I'm going to go ahead and run the simulation for this particular design. And one of the things you notice is that you can see the cycle by cycle power activity. Each dot here represents one cycle, tells you what your peaks are, and and the red one represents the average. Now, when I look at the state plot, what it's showing me over time, I'm going to just zoom into a particular region over here. As you can see, these correspond to the pre-charge and the activate, and these correspond to the write cycles, and these are the refresh for all the different blanks. Sorry, for all the different banks. So using this, you can actually determine what is your overall power consumption for the particular system. Now, moving on to looking at a little more about the role of power analysis, first and foremost, the power analysis at the system level impacts a lot more than just the power consumption or the battery. It impacts your overall cost because it's going to impact your thermal design, your cooling. It also impacts the size of the battery you require, what's the weight of all the associated circuitry. So there's a huge impact for not doing power analysis. A lot of consumer products use this methodology, which I'll talk about a little more, to really gain a better battery life. If I have say an adventure camera, how do I go from about 1.5 hours or 90 minutes of battery life to 120 minutes of battery life or 2 hours? The way to do it is really looking at an intelligent use of all the devices. I can change my read and write rates to memory. I can change the attributes or the frame sizes that are being processed. How does that change the power, but at the same time, what is the impact on latency? Of course, the other one is looking at power gating, looking at power management systems, things like that. The other piece of it is really about creating a three-dimensional view, which is power, performance, and functionality, and being able to do trade-offs between all of them. The final one is that really about putting the input for mechanical and for the testing. Mechanical for temperature versus thermal effect, testing for what are the kind of power states that are required and what's the expected output as well. Now, here's one design where we're looking at an architecture where if you have a variety of clock speeds for both the processor and the peripheral. You can look at what your overall power consumption is for each one of them. And then you can see what is the latency of the task, what is the range. It goes from about 2 microseconds to 12.5 here. Notice going between, increasing the peripherals can really add much to the performance. But notice when you jumped it up here, it went for a little more than 2x. The performance did improve considerably. Now, one of the things you notice is the cycles per instruction didn't really change that much, going from 166 to 400, though the MIPS did more than double. So one of the things that does happen here is, if you look at the energy efficiency rating, the 400 megahertz actually had a better rating than the lower clock speed architecture. So which means what it's telling you is that having the higher one actually gave you a better performance and also gave you a better power efficiency. Now, how does VisualSim Power Analyzer, which is what I was showing you as a demo, really work? First and foremost is it's not based on just a static. It's based on the dynamic activity based on use cases. So for example, you can take as your starting point your existing system with the use cases, which in the earlier case I'd shown you was an imaging, where you're looking at, read frame, do an ISP, do a H.264, do an encode, do, maybe send it out on a Wi-Fi. So what is the power when you do that activity? Similarly, if you're doing, like, say, an open switch on an FPGA, you can look at aspects such as, what happens if I do my TCP offload? What happens if I do my, say, like OSPF? What is the power consumed? So it's really looking at the dynamic activity. Now, what is required to get VisualSim Power Analyzer up and running? First and foremost is you need the power level for each state. The second is you need to know what the transitions are and what is the controller speed, meaning what is the time that it takes when you go from a lower state to a higher state, how many cycles. The third one is there any dynamic nature like a frequency scaling which may cause the power table to be modified. And the last one is really looking at what are the attributes, which in this case can be the state and power levels, the battery level, and the charge of the battery. Now, what are the outputs that you should get out of the system? The outputs that you get out of VisualSim are things like, what is your peak power, your instant and average power. You get information like what is the battery charge and the discharge, how much was the energy consumed per device, things like that. So it's really you get an accurate capture of the activity in your entire system. The mentioned system can be a semiconductor, can be a processor, can be even a spacecraft, can be an aircraft, can be a high-performance computer, can be a networking device, or it can be an automotive. Now, how does this work? What you see over here is a block diagram, which this one, for example, can be your demodulator, can be your encoding, can be the FEC, and each one of them is associated with multiple number of power modes. So as the system goes through, say, a buffering, gets a sampling, does some execution, comes out, the block itself is going to be at different times going to be in these different states. And VisualSim actually captures cycle by cycle what is happening in the system and computes the power associated with that. Now, when you look at a detailed power management, what you're seeing over here, for example, is you have, say, an init state from which you go to an off. So this essentially is a finite state machine that is creating the transition between the different states based on activity within your task or your application. Now, let's take another view of power. And for this, I'm actually going to go over to the demonstration. And what I'm going to do is I'm actually going to show you a block diagram where we have 4 concurrent tasks. And they're all being fed into a multi-core processor with 4 cores. I'm going to go ahead and run a simulation. One of the things you'll notice is that every cycle, they're being executed here. Each one of these colors corresponds to the different cores, and the length here is the duration of time that each of these tasks are executing. What you see over here is the power, which shows you the instant power with a peak value of about 2.5 milliwatts, and you can see what the average power is. And you can see what the discharge is and what the latency is to complete each of those different tasks. We're going to take the exact same design. The only change is currently all of these are executing or they're starting off at the same time, which is right here. They trigger at the same time. What we're going to do is we're going to change this where they're going to be shifted by a small amount of time, which in this case is about 30 microseconds. I'm going to go ahead and rerun the exact same design. But one of the things you're going to notice is the number of times you see this peak has reduced considerably. What you do notice is that the power level stays about the same. But here what you're going to notice is I see only 2 colors. Matter of fact, yeah, I just see 2 colors, which is the black and the green. The reason being is that now because of my shift, I'm not running one on top of the other, one on top of the other. I'm just shifting it off so that these tasks are not all arriving at the same time, which means I only have a few scenarios where I have this peak loading. Most of the time, the power is actually considerably lower. And also what it's going to do is it's going to reduce my my latency as well. And actually it forms a much more tight boundary or a tight range as opposed to the earlier design. So one of the things that your power analysis can help you do is help you evaluate between, say, for example, your tasks where your software scheduling changes from 1 to a different type of an offset. And you can see what the latencies and the power consumption is. Another attribute is you're really looking at the overall trade-off. So you're looking at that from a more textual diagram. You see the baseline was about 6.15 milliwatts. The modified is 2.3. The average was going from 2.8 to 1.4. Here's 1.5, 1.4. So notice the modified, the range is actually much flatter. So which means what has happened is that I no longer have these huge spikes. The average is a very smooth curve. Similarly, you can also see what the range in your latencies are between the two architectures. So what you've done is you've done a power performance trade-off on your overall architecture. As always, just to remind you, go ahead and feel free to ask any questions. There are people standing by to answer all of your questions. A quick note on some of the libraries that are available in VisualSim. There's not a complete list, just to kind of highlight to you the libraries that are there. All of these libraries come pre-configured with power and with timing and with functionality. So what happens is for you to construct a system level model, you just need to drag and drop these blocks together and you can assemble up your whole architecture. The nice thing about this is that you don't actually have to try to build up the different building blocks from scratch like you'd have to do in RTL or C code or things like that, but rather you're just dragging and dropping them and connecting it up like in say this in this particular architecture, just using pre-configured building blocks, and each one would have a unique set. So for example, if I click on the axis bus, it has a unique set of attributes to create your particular implementation. Similarly, if I go into the hardware accelerator, it's going to have its own components that are used to describe what this particular hardware accelerator is going to be doing. So every block has a unique set of attributes that you can utilize to be able to configure it to meet to make it match exactly your implementation. Now, in conclusion, what I really want to talk about is that the power and time must be really evaluated in the same model. So really, you can make your system architecture goals and refine your architecture based on a combination of the requirements, not do individual trade-off, but rather do a power performance trade-off. You want to simulate the design for dynamic behavior, workloads, and use cases. The dynamic nature will really provide you a very accurate representation of your design. So for example, some of these architectures that I was showing you as a demo here, for example, the instantaneous power on a dual channel DDR, if you take the Micron's data sheet with the analytical information and apply it into this model, you will see that for a particular design of a Micron memory, you will get 99.7% accuracy in the power consumed. In most designs, we can be over 90 to 95% accuracy, of course, depending on the level of abstraction that you assemble the model, to be able to effectively get your power budget or your power numbers. That's one of the motivations to migrate to a system level power modeling or power analysis, because you can very quickly create models, you can very quickly be able to do these analysis and also get extremely accurate results. As you saw, a whole 20 milliseconds of an entire camera design took less than 36 seconds to run. So you can run a large number of configurations and get results back. The other aspect of it is really looking at possible design bottlenecks. Design bottlenecks may be that, I have 220 watts of power. How many boards can this chassis handle? And if there are more boards, how do you actually do trade-offs such that you keep the power below the 220? The other aspect of it is looking at where your system bottlenecks are, and like for example, say your bus. If I move to a lower clock speed, So I can reduce the power consumption or make it a thinner bus. For example, the thinner bus will actually a narrow width of a bus could actually reduce the the power, but it might impact the performance. How much is that impact? Is it still okay that I can go ahead and keep doing my design? The last one is really you now have a power model that can be distributed across both your customer and your development team. Really something that you can actually evaluate over over the entire product development cycle, and even like with your evaluation with customers as well. So one of the things that is a natural follow through of this methodology is really generating documentation out of these particular designs, and then be able to embed that into your own documentation. So you generate the documents and then you embed the models right in the documentation, so someone that's viewing the documentation can actually run simulations right from within the web browser. They don't need to have the software, they don't need to know VisualSim, but rather they can actually run simulations right from within a web browser, which makes it essentially look like it's popping out of the documentation. So what I'm doing right now is I'm actually going to our website, which is mirabilisdesign.com, which is located in Florida, and it's going to actually bring up a block diagram of a model that I'm running. In this particular case, it's a dual core with DSP and an IO and multi-bus and bridge architecture. So you can look at it as a full system, and just coming up in a second. Um, as this is uploading from Florida. Now this will be really in your context a private cloud within your environment, as opposed to something that's located in our environment. And when this pops up, you will actually be able to see a model that looks identical to your architecture or to your particular design. Now there are people standing by. Feel free to go ahead and keep asking the questions, and they'll be more than happy to answer those questions as well. So as the model comes up, really to conclude, one of the things is that we're actually going to be exhibiting in early April at the 32nd Space Symposium in Colorado Springs, Colorado, booth number 1103. So if any of you are in that part of town, please come by and visit us, and we'll be happy to demonstrate and show you more information about this. Thanks a lot for your time, and we'll continue to be here answering additional questions and bring up the model as it comes along.